welcome to this session. We're going to talk a little bit about shortcomings of intrusion prevention systems. Well, IPSs. I guess all of you love IPSs. Well, with the IPSs, there have been a lot of mess, a lot of marketing. It's like kind of passion. You know, people hate it, people love it, people sell it. That's my case. So I think that before we start with some technical stuff, it's kind of interesting to define the rules of the engagement. So first of all, you will know who's talking. Then what to expect to talk about. Also, it's important for you to know what you want when you're dealing with IPSs, because you can do many things, we'll see. You have to remain realistic. And last but not least, don't trust anybody. So first, who's the speaker? So my name is BIDOU. I'm a Radware employee. So Radware is an IPS vendor. And I am an employee. It means I'm kind of lobotomized slave. But anyway, I've been involved in a lot of IPS testing for many reasons. Either for, well, you know, independent or so-called tests. I've been participating to some test labs for magazines, for partners. Of course, I have tested some IPSs from the competition as part of the competitive analysis. Where I worked with some research labs from telcos, universities, and whatever. So even if I'm not supposed to be maybe so neutral, I've got quite a good view of what can be done with IPSs. What are we going to talk about? Well, I'm going to focus on devices which are in line, and devices which purpose is to block traffic, malicious traffic. That's it. Okay, and I will try to remain in the real world. It means that the purpose of the game is to have an IPS on your network. It means in production, that means it's going to be active and protect your network. So any kind of bypass technique, any kind of attacks, etc., will be completely real. It's not theoretical. It's not, maybe in this case, if I've got this signature and this and blah, and then maybe I can't. No, it's real-world experience. So of course, we will see technical issues, and we'll see that is directly linked with some, well, human issues, organizational issues, and of course, money, finance. Well, so, oops. Okay. What do you want? Maybe you just want this perfect box, you know, this box that is going to secure your network, 100% sure, no management, no updates, completely reliable and stable. So I think that if you still believe this kind of box exists, you still believe in Santa Claus. Also, stop reading adverts in magazines or whatever, okay? Maybe we want to prove that we can bypass an IPS. It's just a waste of time. I mean, it's something which is obvious. It's a security device, and we'll see that there are many ways to bypass this kind of device. So you just take the risk to prove that you're not able to bypass it. Let's say you tried and you didn't make it. Then, man, I can tell you, you're not good. And, well, so maybe you want to test the IPS just to understand its limitation. Understand which are the weaknesses you still have in your network. And yeah, that's it. That's the purpose of this talk. Well, the truth. Or part of the truth about IPSs. What do you want an IPS? So if you tell me just because it's a hype, because it's cool, I don't think it's a good idea. Whatever vendors will tell you, IPS will introduce latency and they generate false positives. The rate may be very low, latency may be very low, but you still have these 2 points. So no, IPS is not cool. Maybe you heard about this new technology with heuristics, correlation, statistics, and blah, 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 and you absolutely want it on your network. So if it's the case, I think that's just because you're a newbie in the business. Okay, all the vendors have these kind of terms, usually to define very basic mechanism. And then maybe it's just the best case here. If you want to go out with a sales girl. So maybe you've got a chance. Just go on the Radware booth. Maybe you've got a chance there. Okay. Also, when dealing with IPSs, especially with IPSs and all this kind of technology which is new, all vendors want the best of the market, so they're ready to do anything just to get the market. Be completely paranoid. Don't trust the rumors. You know, I heard that this IPS got bypassed and blah, blah, blah. Third-party test results? No. I can tell you. Nobody is really independent or innocent. I've been to those tests, I can tell you. Mailing list? Well, just look at the mailing list like IDS Focus or this. Oh, come on. It's only vendors. And don't trust consultants. Sometimes they may look cool, okay, but they're just lobotomized slave. After all, they're all alike. So, what's an IPS? And that's my definition. And this is this kind of device we're going to work on. An IPS is something that is going to interfere on the network. Whatever a vendor says, if it's going to block traffic, if it's in line, it's going to interfere on the network. It's going to enforce some kind of security policy, maybe some bandwidth management, reset traffic, generate SYN cookies, whatever, is going to work on the network. Also, something which is very important, I think, is that an IPS is not an IDS with tunings. Okay, no. Why? Well, IDSs are just created to report. They are going to report you a lot of information you should correlate with some other information you get from your IT infrastructure. An IPS is born to kill. It's just here to shut the traffic, hopefully malicious traffic. Reporting with IPSs is just for management and for investigating false positives. That's it, theoretically, of course. And IDSs do have some kind of paranoid mode, you know, just like shouting for almost each and every packet. Oh, I saw an HTTP packet. Maybe it's SQL injection. I'm not sure, but it's still HTTP. I don't know. Of course, it's not possible with an IPS. This kind of behavior with an IPS will kill legitimate traffic. An IPS also has to block everything on the network. And the best example is that, let's say you're playing with Snot. You know, this tool that just takes node signatures and send them over the network out of any kind of sessions or whatever. It's a big mess for IDSs. If they don't have their stateful engine ready and, well, quite working, you will get it completely flooded. For an IPS, you don't care. This kind of packet has nothing to do on the network, so it has to be shut. So if you tell me, well, the IPS did shut this packet, but it's a packet out of a session, out of a TCP session, so blah, 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 blah. So what? It has to be shut. It's nothing to do on the network. So it's completely different behavior. And just try to mitigate denial of service attacks with an IDS. Okay? So just keep in mind that's completely different. So when I say I'm going to bypass IPSs, I don't say I'm going to bypass IDS. That's completely different. So, weaknesses and limitations of IPSs. I did identify three main causes. First one is false positive. False positive is the worst that can happen on your network. Okay, so it means that you're going to need very, very accurate signatures or mechanism, holistic mechanism or whatever. Okay, and we'll see a good example of this kind of signature we can get on IPSs with this OC192 DCOM exploit, which was used just for blaster war. And we'll see that some signatures looks completely dumb, but at least you're sure we'll not have any kind of false positive. Also, most of the time, vendors are going to tell you, I've got 4,000 signatures, 10,000 signatures, and as many as you want. But if you go and see all those products which are in line into production, because I told you I'm interested into the real world, then you'll see that's like 200 only that are activated, or recommended for blocking, which means that the other signatures definitely suck, okay, and generate false positive at high rate. So false positive, we'll see, is one of the main reasons why we'll get a lot of vulnerabilities and weaknesses into IPSs. And performance. So performance, here we've got problem with latency and jitter. And for this reason, IPSs will have to do some choices. There we'll see a lot of performance versus security trade-off in favor of performance, of course. And last but not least, and maybe the most important at the end of the day, is the position of the CSO. Okay, this guy first wants to ensure security of his job. Okay, then in this case, packet loss is not recommended. Okay, when you start to lose packets from voice over IP, from your CRM, ERP, and all this stuff, it's not good. So I tell you, this is a very, very important point. So, big families of technical shortcomings. I did just divide it a little bit, the kind of weaknesses I could find. So you've got, first of all, what I call conceptual issues. It's just the fact that because an IPS is what he is, he's got weaknesses. You will see it. Sometimes there's nothing you can do. That's life. Signature issues. So that's very interesting tricks. We'll see about that. Kind of detection engine, all this. That's a lot of potential weaknesses. Hardware. Hardware is very important. We'll see how come sometimes you have to do some choices. You know they are not good, that's your only chance. And once again, this story about performance versus security trade-off. So let's start with a quite simple conceptual case. Just an example to show you what I think is conceptual weaknesses. As we said, IPSs are going to interfere with the traffic. So at different levels. There are many levels where IPSs can work with the traffic. First of all, just the way they're deployed. Sometimes they perform some routing, address translation, reverse proxying, whatever. So here, yeah, you've got interaction with the network. You're going to create packet, change packet, or whatever. Also some kinds of protection mechanism. Like when you generate SYN cookies, yeah, you generate a packet. When you're doing some protocol inspection and you're just handling the session on behalf of the server, then you're generating packets. When you're performing some kind of targeting, you know, this kind of sticky honeypot, so you're generating packets. So you interfere with the traffic once again. And of course, when you react to intrusions, if you send resets, if you limit the bandwidth, or whatever, here you're going to interfere with the packet. So there are many ways, many ways to identify an IPS which is online. And just because it's working with the packets, creating new packets, we'll see that we can track changes during a session. We'll see that TTL is not consistent anymore. Maybe we've got some problems with the IP ID, the Windows side, some MAC addresses when we are working on a local network. So many ways to identify. Also some kind of anomalies, which are, well, it can be at network layer, application layer, many ways, just to see that, this web server is like, well, it's behaving like, I don't know, Apache. I got the IIS banner and a lot of .asp pages. That's weird, no? We'll see this kind of example also. And well, at the end of the day, when you've got all this information, okay, I've got the second generation for ISN. I've got a good idea of the IP ID, well, TCP window size, etc. Maybe just with mechanisms such as passive OS fingerprinting, we can guess what is the nature of the IPS which is online. So just to prove this, I wrote a very small and stupid program, which is called HTTP IPS detect, which purpose is mainly just to listen to the packets sent back on the network. So you send the SYN, we'll get a SYNAC. We're going to listen to the SYNAC and all these kind of packets. And then just analyze and provide a good view of, well, some TCP fields which are interesting, or IP fields, like TTL, IP ID, Windows size, etc., etc. And we'll see that with just 2 URLs, there are many ways to detect different kind of IPSs and behavior. So a very basic standard URL, just getting the home page, and then very old exploit, you know, this colored stuff. So quite stupid. And let's see some results. First of all, I'm going to, well, just detect a layer 7 firewall, you know, what we call these layer 7 application IPSs, whatever, which usually work as a reverse proxy. So here I just launch the baseline, I get the home page, and I see that the IP ID mechanism, okay, IP ID is generated first is 0, and then you've got numbers which are incremented. So this is typically a behavior from Linux. And then I see that the server, the banner, is Microsoft. Okay, this is a little bit stupid example. You're going to tell me I can change the banner, etc., etc. Okay, just to show you that we get some kind of interesting information. Maybe a little bit more interesting, SYN flood protection. Let's say somebody here is working with, well, some SYN cookies. So I send the SYN, I receive a SYN-ACK, and I see that the TTL started at 64. Then I keep on launching my request, and I get the answer. And the answer now is a packet which has been generated with a TTL, original TTL of 128. So we see that the system that sent me back the SYN-ACK, with probably a SYN cookie, I guess, and the system that answered and served the web page are not the same. So I've got somewhere an IPS on the way. With the TTL, I can calculate the distance, see if it's on the same network than the web server, or maybe 1 or 2 hops before, and get ready for maybe some kind of insertion. More advanced again, pending sessions. You know this kind of attack where you just connect to a port like port 80, okay, SYN, SYN-ACK, and then you just try to keep alive the session without sending any command. So at the end of the day, if you do that maybe 10,000 times, server is not going to accept any more connections. So, well, basic protection is just, you know, to behave for an IPS to behave a little bit like proxy. You know, just getting SYN, SYN-ACK, ACK, and just waiting for the first command, HTTP command. So if he doesn't get the command, it doesn't transfer the session to the server. And this is what happens here. Okay, I received the SYN-ACK with TTL started at 256. I received the ACK of my first command, maybe my get slash, with once again this TTL, and then the rest of the session is done with a system which TTL started at 64. So once again, it's another system, and we detected this IPS. And well, maybe easier anyway. It's just when you send an attack and you get a reset. You see at the reset, just have something like, okay, it's different TTL here, and completely different IP ID. So, okay, for sure, there's a system on the line. So, you see here, this very basic example to show that IPSs, whatever you do, we saw layer 7 firewalls, we saw reverse proxies, we saw SYN cookies, session pending protection, all this, and each time there was a way to detect it. So it was different products. Some of them I don't even know, I just tested on the internet, but it's very easy to detect, okay? So big picture here, problem is the environment. Because how can you hide your IPS? It must behave exactly like the remote system. So, okay, if you just protect maybe like one web server, you can try to copy and, well, to patch whatever just to get exactly the same TTL, exactly the same kind of sequence number, IP ID generation, all this, that's okay. But I was talking about something I call real world. In the real world, you don't buy an IPS to protect one web server. You want to protect your infrastructure. Maybe 50, 100 servers, thousands of workstations. So you're going to tell me that for each and every IP address, you're going to tune your IPS just to say, well, I'm going to make sure that we've got exactly the good TTL, the good IP ID, and it looks exactly like the server? No, it's not possible. So we saw this for some TCP and IP fields, but we've got some problems also with MAC addresses. When you're performing some NAT and you're working on a local network, we see that the same IP address is going, well, different IP addresses are going to answer with the same MAC address. Then you detected the NAT, very easy. Stack internals also. Why? Because systems do behave differently when handling, well, fragments, when handling all this kind of stuff. Okay, so there are different sizes of tables, and this is the kind of difference you're playing with when you're doing some insertion attacks, exactly the same. You will see that this stack is going to start dropping frags after maybe 30 seconds. and then the IPS is going to just drop it after 3 or 4 seconds. It's usually for performance reasons. Here, once again, you've been able to block it, or to detect it, sorry. And that's true also at application layer. Okay, just think about all those HTTP request smuggling, response splitting, and all this. Okay, each time it's because you can bypass IPSs, you can corrupt cache, you can compromise some sessions in some cases, just because the proxy or the IPS or the web server don't behave exactly the same. Well, it's like, you know, recently there's been a way to bypass some filters that were not really able to detect a URL, which is still valid for the server, but not for the IDS. Once again, it's the same. So in terms of solution there, well, there's no solution. That's what I said. It's not possible to maintain this kind of infrastructure. One server, well, let's say you've got a few servers and you're going to patch them. Maybe something is going to change into the stack. And then you have, once again, to go over your IPS and change all the tuning. It's not possible, differently. So maybe the only solution is to run exactly the same system, but then it will be vulnerable to the same attacks. Perfectly useless. Okay, let's talk a little bit about signatures now. Because, well, okay, detecting IPSs is okay, but not so cool. With signatures, there are many things we can do. But first, we have to understand different kind of signatures we will find into IPSs. First, we've got what we call generic signatures. They are here with kind of global pattern to detect, well, generic threats, okay, like shellcodes, buffer overflows, all this, okay? We've got, I include into this category, very basic kind of behavioral signatures, which is like, you know, if I see 10 authentication attempts in less than 1 second from one source to one destination, I say it's a brute force attack. I get it into this category. Then we've got the vulnerability or vector-based attack signatures. So they are going, these kind of signatures are supposed to be more accurate because they are going exactly to sign the vulnerability and the way it's been exploited. So should be quite resistant to any kind of obfuscation, very accurate, but we'll see it's still not perfect. And then you've got the exploit-based. You've got the very exploit, and you want with your IPS to block this exploit. Not no any variant, just this exploit. That's even more accurate. Of course, that's too accurate. And just keep in mind those very important issues: false positive, performances, and maybe evasion. I say maybe because, once again, what's really important for you, if you don't want to get fired, is first to ensure that your network should have good performances and doesn't drop packets. Talking about some generic signatures. We've got very basic and standard patterns, like, you know, just knob sleds, null sleds, all this, usual shellcodes. We saw this kind of very limited behavior, which is just dumb statistics. And here, the problem is false positives. If you're too generic, you're going to generate a lot of false positives. And then you're not going to activate this signature. So, stupid example is just, if you've got 20 times, when you just count null, and you see that you've got more than 20 nulls in a row, you're going to say, oh, okay, that's, I think, a kind of shellcode for buffer overflow, I don't know. No. In a lot of binaries, you will find this kind of sequence of packets. So that will be a false positive. Then you have to be a little bit smarter and just say, okay, so let's also sign the short jump, which you will find usually after this knob sled or null sled. And then you've got a good signature. So you see the problem with IPSs, that signatures are far harder to write if you want them to be efficient, if you want them to run into production. And that's the reason why, out of thousands of signatures, only a few hundred are usually activated, then limiting dramatically the real security that provides this kind of device. Also, you've got this security policy and all the customization issues. Okay, let's say that an IDS can shout and say, hey, I see an SNMP packet with this public community. It's not good. If an IPS is doing that and it blocks this packet, you're going to get into trouble. Because usually, that's management. Okay, management is not secure. Your IPS is not here to define your security policy, just here to enforce it. So you see that a lot of signatures, a lot of insecure behavior are not going to be blocked by IPSs. And it's normal, or, well, anyway, that's the way it should behave. With this kind of generic signatures, evasion is usually very easy, because these generic signatures, as we saw, are, well, generic, but they've been worked on a lot, like this short jump after the node sled. So it's pretty easy just to evade this kind of signature with a little bit of changes somewhere. And also, there are always these performance issues that make signatures are going to be as short as possible, and then not going to be so accurate. Vector-based signatures. Here, the purpose of the game is just to sign a vulnerability, sorry. So it's completely independent from the payload, and it needs something far more advanced engines, just to detect it. Because it's not just detecting a few knob slides or all this. It's usually far more, well, advanced. I say, let's see this signature, against this DCRPC DCOM exploit that I get from Snort. First of all, to ensure I don't have any kind of false positive, we're going to try to analyze and make sure you've got DCRPC traffic. Okay, that's, well, pretty dumb stuff, test, but okay. And then what we're going to do is that we know that this vulnerability is the name of a NetBIOS resource, which is too long. So what I'm going to do first is try to find where is it NetBIOS resource. So you see, at this point, here. Whoops. Here, you see, it's the two backslashes, Unicode encoded, that are just, well, we're looking for them. And then from there, we know that the size of the field is coded just before. So we go back like 8 bytes back, minus 8, and then we compare the 4 bytes and make sure their value is larger than 256. If it's the case, we've got the exploit. So you see that signing vulnerabilities is very accurate. Needs a lot of work. It's supposed to be pretty good. I just said pretty good, why? First of all, you need to know that there's the vulnerability. You must be aware of it, okay? So you need some kind of disclosure, some kind of information about it. And also you have to make sure it's accurate enough. For this exploit, I saw some IPSs which has just one signature, which is iSystem activator binding request. So it's completely legitimate connection to this interface, RPC interface. And the fact that it says, oh, we're under attack. That's typically a huge false positive. Okay, and it's not going to be ever implemented. And then this attack is never going to be blocked. Exploit-based signatures. The interest with these signatures is that they can be completely done. Their purpose is usually to block, those, outbreaking worms, mass mailing worms, those major threats, which are very well known. They're propagating, and you just want to protect your infrastructure from them. So here, you don't need an intelligent signature. Just going to see the payload, and this is the case here. I didn't provide the name of the vendor, because it's kind of shame. But anyway, the signature here for the DCRPC DCOM exploit, which is used in Blaster, is simply to, encode the name of the resource here. This is the resource that was called by the war. So the name of the server was something like, I don't remember, NXFB, something like this. okay? So just looking for the name of the server which has been called. That's it. That's stupid. That's efficient against, well, dumb attacks, blind attacks. It's very efficient in terms of performances. You see here, stupid matching, but it's not going to provide any kind of security, or I'd say advanced security. Very, very easy to bypass. So, let's make it clear. What I wanted to do, based on this story about signatures, is just to provide you a small example. I take this very old exploit, signed by everybody. Everybody, any IPS is supposed to block this very, very old attack, that's Blaster. How come you're not able to block it? So I take this exploit, okay, the very exploit, and then I just played a little bit with it. So just like changing the knob sled into increasing and decreasing the EDX register, okay, quite stupid obfuscation, why not? I changed some, well, exploit data, so like the name server we were talking about. And then I play a little bit with RPC features provided by the protocol. That's typical layer 7 protocol. I didn't add anything on it, on top of it, okay? So I do some fragmentation, pipelining. I just play with context alteration. I establish multiple contexts, and that's it. And just we'll see that we'll have to change just the port to remotely connect to get the shell. So from there, I used 3 different IPSs. One is Norton Line, and 2 others are vendors. I'm not going to name, not to get into troubles. And I launched the attack first. So you see they're all in a row. So this whole theory is saying that you need to use different technology just to make sure that if you can bypass one, you will not bypass 2 of them. We'll see that here I'm able to bypass 3 of them. But let's start with the beginning. And here we see that we've got like, well, 6 different alerts which has been raised. First one, raised by Snort. It just, okay, path overflow attempt, so typically the exploit. Then we've got something more generic, RPC decom interface buffer overflow and upsled detected by the second IPS. And the last one is generating 3 alerts. It was quite difficult to bypass it, I must admit. First of all, just a BIDOU which is quite large. Okay, maybe you can play with that. Buffer overflow on Microsoft DCRPC interface, and then the Windows command shell running this 666 port, which has been detected. So let's try to bypass them. First of all, if you want to play with Snort inline, it's pretty easy to bypass it because it's not able to handle multiple contexts. So in this small software, I just activate one feature which is multi-binding. I say I'm going to establish, well, some sessions on some interfaces, interfaces, establish some bindings, and then bind on the iSystem activator and launch the exploit. So first it was just copy and paste from the code of Metasploit, and then I improved it a little bit more. We'll see why. But here it's very basic. It's not able to follow different contexts. So as my exploit is launched on a context which has context ID of, I don't know, maybe it's randoms, but not context ID 0, it's not going to be analyzed by Snort. So that's one. Let's try now to bypass the second one. Problem is the knob sled. So as I told you, I just activate the obfuscated shellcode option, which simply changes, you know, this knob sled into increase and decrease the register, and that's it. I bypass it. Pretty easy. Second one is an option I added, which is alt server, just to change the name of this NetBIOS resource. And we see that this IPS for this signature, or this detection of RPC decom interface buffer overflow, we're just relying on the name of the resource. So kind of stupid and kind of very easy to bypass. Then we move to vendor number 2. The problem here is that, first of all, if I establish too much bindings, I'm not going to be able to reduce the size of the BIDOU, and I will still have this alert about overly large protocol data units. So I needed to edit a little bit the code, so I'm just establishing, when I ask for multi-binding, first of all, a binding on an existing interface, or I will raise an alert, and binding on I-system activator interface. So just 2 bindings instead of something like 15 that we've got from the Metasploit code. And then I play with fragmentation at 2 layers. You see the frag size option is just playing with, well, the TCP data size. It's 256 bytes. Okay, into this, I'm going to play with DC RPC fragmentation. This is the RPC frag size option. I'm going to generate, DC RPC packets or data of only 32 bytes long. It means that into a single TCP packet, I will have multiple DC RPC fragments. That's kind of pipelining. And here, well, we'll see that I bypass all signatures, except one, of course, which is for the remote Windows command shell. So first, I tested with, changing the port to like 23, because like Telnet, maybe it's not going to detect it. But of course, it detected that it's not Telnet opcodes. So I had another ID, and we see it's typical shortcoming. Just set remote port to 282, which is SSH. And here, no more alerts. So we'll see why, but usually it's for performance issues. You want to save time, and you know that port 22 is SSH is encrypted, so you don't analyze it. And yep, you bypass it. So here you see that this very, very stupid exploit, well, not stupid, it was brilliant, but very old, with few minor changes. I'm not the king of reverse or whatever, so I just got the code and changed some stuff in it. I just played with a little bit of layer 7 features. That's features from the protocol. I did not invent them. And then I got it work. I bypassed 3 IPSs in a row. And it's not all. I mean, we've been just playing a little bit with some layer 7 stuff, a little bit of fragmentation, payload encoding or whatever. But you've got all those representation tricks, which are very important for DC RPC, but all the, well, encoding you can find like in HTTP. And you've got this problem with the URLs. You know that, well, some basic evasion techniques, just encoding the URLs. But you've got some tricks. If you see the first one, you see that from the PHP BB, somewhere in the URL, I just double encoded the 2 Bs. So here, a signature analysis engine must be able to understand that here, in this kind of case, for this kind of signature, I must be able to decode and then to analyze. In some other cases, it's not I can do that. Okay, just try the other one, the other exploit. Okay, here you see that I did a double encode, the single quote and dot. This is part of the exploit. It's not something I did encode. The URL you're launching to exploit the vulnerability is written like this. So you need, or you should need, an engine which is able to know when to decode and normalize your URL and when not. And that's a problem. That's a problem in terms of performance, in terms of signatures, writing, time. That's a problem. So it was about signatures. We saw that a lot of weaknesses there, pretty easy to bypass, but it's not, or maybe there's even worse. It's hardware issues. So of course, that's the basement of your system. You know all those IPSs, which are running multi-gigabit, real-time, 100% security performance, and blah, blah, blah. Okay, so they're relying on the hardware. And this hardware, we wrote many kind of designs. We've got many kind of, well, devices or, well, chips we can use, like, well, generic CPUs, ASICs, network processors, and each and every of these kind of devices have internal architecture and specificities. And we see that in some cases they will be good at performing some operations and very bad for some others. Also, you have a choice between just one component and then, well, distributed architecture with many components in different kind of architecture like pipelining, parallel, and so on. What is important is that you must understand that vendors know advantages and drawbacks of all of these. We know that some network processors are very good at handling small packets. Some others are very good at handling large payloads, but it's not the same. We know that with this ASIC, I will be able to do some regular expression. I will be able to speed up some NFA engine for regular expression, which is very good. Some others will hardly deal with some kind of encapsulation, etc., etc. Don't think that vendors are stupid. Just know that. I know that very well. Okay? And then I think, once again, the most important is cost. Vendor knows. But come on, if I tell you I've got the best IPS, very good performances, any kind of packet, okay? But that's $1 million at the box. I'm gonna say, no, come on, it's not possible. I've got to lower the price. And then I have, first of all, to make some choices. And say, I'm going to use this network processor. I know it's not good for this kind of operation, but good for this one. And this kind of ASIC, et cetera, et cetera. Also something important in cost. That's the acquisition of the chips. That's one thing. The second thing is basically the fact that you have to develop, maintain your software. That's high cost. So when you say, okay, I've got some kind of chip ASICs, it's pretty good, but then in terms of development, it's a mess. Okay, each time you've got to debug, it's terrible. Then you say, okay, let's go on just one single CPU, Intel CPU, run on Linux. In terms of cost for development and maintenance, it's like nothing. That's something very important you have to keep in mind. So just quick reminder of, well, these components. CPU, okay, you know it, everybody knows. Very generic, low cost for acquisition and development. ASICs, dedicated to very specific tasks. So once again, vendors know what they choose this ASIC for, okay? If you program it properly for the proper function, it's going to go very fast, okay? But, well, it's kind of higher cost anyway. And then you've got network processors. Network processors are pretty tricky, you know? They're supposed to help you handle layer 3 and layer 4 operations. Like, and we're understanding like TCP, well, port session, all these generating cookies, etc., etc. But here you've got a lot of architectures which are different. And that's multi-core systems, but we'll see that. A lot of tricks. In terms of architecture, when an IPS vendor is designing the system, you've got a choice usually between pipelining and parallel processing. So parallel processing is just, well, each and every component is going to perform multiple tasks. Okay, the interest is that you don't have bottleneck usually that you've got in pipelining architecture. Pipelining, if there's one component that takes too much time to perform an operation, okay, you've got bottleneck. Everybody's waiting. With parallel, okay, it's far more, it's getting faster. Wow. So you get less throughput, but you get also less latency and less jitter. Pipelining is just the opposite. Okay, it can go very fast as long as there's no bottleneck. Okay, you will get better throughput, but you have some problem with latency. It's normal, because each time you've got a piece of data and you forward it to the next core or the next component, then you've got an overhead just for, well, transmission, context change, etc. So in terms of latency and jitter, we'll get more. And then, of course, you've got this generic versus specific, okay? Sometimes you would like just to say, I've got some CPUs, very generic, very easy to develop. That may be a problem. Also, if you have multiple components, it's harder to develop. Okay, but usually it's the only solution. Because if you just have one CPU, then usually slow path operations are very quickly going to flood your system. And then you got no more performances, and we see how we can bypass them. Well, just a short talking about the network processors. This is what I said. You've got different kind of architecture into these chips. They've got multi-cores. Some of them handle the slow path operations. Some of them don't, so they need an interface. It's cost in terms of time. Depends on, well, what you want. The real problem here is that, let's say you've got some network processors into your IPS, okay, and you say, I want to get good performances with, like, short packets, okay? So you say, I need a system that should be, like, in pipelining. Pipelining is very good for that. But then, in the middle of this traffic, you've got some payload. That's normal. I mean, usually, you've got some legitimate traffic with some payload, and then performances are going to go down. So as a vendor, you've got a choice, usually, to say, I'm good at for small packets, and usually for tests. I'm good at handling large packets. But then, with small packets, I will not get very good performances. So that's typically the shortcoming you've got here. And that's still a question of cost. I could say, well, I can have these two families of network processors and a system to classify the traffic, small packets, large packets, and on top of it, another system to rebuild all the data, flags, all this. Okay, but it's far too expensive, I can tell you. So usually it's going to be a simple matrix that takes into account, well, performance, marketing and cost, and then security. So vendors are going to make a choice. They're aware of that. We've got also some very funny examples of these choices made by the vendors. A few years ago, a network processor vendor used to sell to IPS vendors, or all these security device vendors, a cheap network processor which was said to handle, 802.1q VLAN tags. So everybody said, okay, let's build our IPS on top of it, on IDS also, it was all the same. And the problem here is that it was good for IDSs because it was able to read these tags, but it was not able to rewrite them. So it means that on your IPS, could read the data, could not send it back on the right VLAN. So it's just black hole. And it's very funny to see that at this moment, like 2 years ago, many vendors had some issues with VLAN tags. There's been some, discussion, rumors about they don't handle VLAN tags, or these, they don't handle VLAN tags also, etc., etc. I can tell you that at least 2 or 3 vendors had the same problem because they use the same hardware, same architecture, and just made the same choice at the same moment. It's like for the bypass. Bypass switch, purpose of the game is if you've got any hardware or software issue on your IPS, then the bypass is going to be activated, and the traffic is not going to go through the IPS. This is usually what people want, because as I told you, as a CSO, first of all, just want not to lose legitimate traffic. So it's very expensive, especially for fiber ports. So usually vendors are going to rely on third-party vendors just to sell this kind of equipment. And it's very funny to see also that 2 or 3 vendors still have the same product for bypass. So I'm not going to tell you the URL, but you've got a URL of this kind of bypass switch vendor, and then you just add at the end of the URL the name of an IPS vendor, and you got the product. And then you add the name of another IPS vendor, got exactly the same page, just with another logo. Okay, so everybody uses the same. Okay, all the vendors are aware of that. All the vendors are working on the same basis. And also it's not hardware, but it's kind of same story. Bugs. Recently, you've seen this way to bypass a snort and some URL investigation. I'm just curious to know how many vendors, it's mainly for layer 7 firewalls there, some IPS also, did just update a few days after that, just because they were patching something, maybe patching their snort engine, and maybe even worse, how many did not patch? Because a lot of vendors just rely on snort, so those that didn't patch are still vulnerable, and I found some. And then, of course, performances. This is, I think, the main reason why you've got limitations and why it's quite easy to bypass IPSs. You've got this, the need for speed. You need to go fast, very fast, okay? That's the rule of the gigabit. When you go to a customer, they said, I want a box that's going 5 gig. Okay, it doesn't really know what it needs for that, but okay. And latency is now the value, the metric, which is good for us. And sometimes even values are kind of stupid. Are you sure you can make a difference on your network when you've got like 30 microseconds of latency against 200 microseconds? Maybe for some traffic, not all of it, definitely. So you've got this throughput. That's holy grail. You've got to get the best throughput as possible. Then, okay, you're a vendor, and you know that, first of all, the guy in front of you is probably not be able to test properly the IPS. And you also know that he will not buy anyway if you don't handle this bandwidth. He tells me he needs 2 gigabit, I'm going to give him a product that does handle 2 gigabit of traffic. Okay? So what do I do? What are the issues? Well, interface cards, network interface cards, no. Switching fabrics, no. All the rest, yeah. You've got performance issues everywhere after that. So when you go into physical components, you've got, well, bus speed, memory access, all this is going to impact performances. In terms of software, all the features you can have, you know, like, okay, some stateful, analyze signatures, generate SYN cookies, and do some bandwidth management, and, well, behave like a honeypot, all this. No, come on, that's big, big use of resources. So, in a nutshell, what we want is security which is transparent. And at the end of the day, you say, I like better have no security than traffic disruption. This is the reason why you've got all those bypasses switched. So you cannot accept any kind of performance impact. So there are some trade-offs which have been made by the vendors. Some of them are visible, like, you know, this application port selection. When you say, I'm going to analyze HTTP traffic, usually you've got a choice, and you're going to say HTTP traffic is going to be analyzed on port 80, port 8080, port I don't know. Sometimes it's going to be a little bit different. Okay, it's going to be like, well, like this North possibility just to say, I'm not going to search for shellcodes on port 80. Okay, so you just save resources. Okay, and sometimes it's even into signatures. I'm just going to say, this signature, I just look for it if it's a packet going to port 80. Same for fragmentation. And it's very funny to see that the more you go into upper layer fragmentation, the less options are visible. For layer 3 fragmentation, you've got a lot of options. Size of the frags, maximum size, number of frags, amount of time it's kept in memory, all this. Layer 4 fragmentation, which is just like having a URL in 2 different packets, sometimes it's just a checkbox. Sometimes it doesn't even exist. And layer 7, nothing. I think I never saw any kind of option to play with this ERPC fragmentation. Okay? So that's problem. We see that more and more vendors are not going to just implement this kind of feature. It's too greedy in terms of performance, and all in all, okay, that will provide good security or some security. That should be enough. And you've got some others which are kind of less visible, like some operations that use a lot of resources, like just calculating for checksums. What for? Okay, remote systems are going to do it. So sometimes layer 3 or layer 4 checksums are not going to be calculated. So it makes it very easy to do some insertion there. Mid-flow traffic detection. Follow all those sessions and sequence numbers. That's boring. That's taking time, memory, resources. Okay, maybe I'm not going to do it. Firewall is going to do it somewhere on the infrastructure. I don't need it. Okay. Well, when you generate SYN cookies, we'll see that you have to be pretty careful. Else, your system is going to be protected against SYN floods. But it's going to be ready to be spoofed. And that's another problem. And well, so sometimes all this stuff are presented as some options hidden just to make sure customer is not going to activate them. Sometimes they don't even exist. Okay, just to make sure. I've got also this one, which is maybe the most important, that's offloading. As I told you, the problem is performance. So what's happening if I'm running out of resources? If I'm starting to lose some packets? If my resources are reaching like 80%? So usually there are some mechanisms on IPSs that are just going to forward the traffic without inspection. So there are different kind of options. Sometimes you're just going to reduce the number of signatures you're going to apply to a packet. Sometimes you're just going to say, okay, traffic is bypassing during maybe 10 seconds, and then I will just see if my resources are still okay. So you've got this way, and it's a pretty easy way, you know, just to bypass an IPS. It's just to, well, just stress it. And when these resources are going to reach very high utilization, usually it's going to bypass the rest of the traffic. And then, well, just launch your attack, you're not going to be detected. We see some examples there. An example of a little bit more detailed example of trade-off you can find. SYN cookies, remember the problem? Is you got a SYN, you receive a SYN, you're going to generate a SYN hack, okay? You want to protect your servers. So you're going to generate a SYNAC, but you don't want your TCB to be overloaded. So you're going to generate a sequence number in your SYNAC, which is calculated based on some network information, like source port, destination port, and all of this. Okay, so your sequence number is just a function of these network parameters. Well, that's very easy to guess. So here, you're spoofing already. So what you're going to do is to use a secret seed and use a one-way hash function, so that you make sure that SYN cookie that's going to be generated cannot be pre-calculated by somebody. We cannot guess what will be the SYN cookie, well, sequence number, sorry. Okay, and then, well, you've got performance issues. Those one-way hash function, I'm sorry, but it's pretty greedy. So you would like to use some function which accept pre-calculation. And there comes MD5. MD5 is okay. But you know that we saw some collision issues and all of this, but you can say that, okay, maybe enough. And this is this kind of trade-off. Well, sometimes the trade-off is just to say, well, don't really need this MD5 stuff and all this, just generic SYN cookies, and that would be okay. And then you've got these invisible trade-offs. That's even worse because you don't know, and you have to like audit the box like a black box. Usually it's based on signature, so that parsers, how to analyze protocols. Okay, how do I analyze HTTP, SMTP, FTP, all this? How do I analyze context? Okay, how do I guess that this is a URL, this is a mail attachment, or whatever? And then the same, like all vendors says, I've got regular expression. Which kind of engine? DFA, NFA, which family? PCRA, something else? Where from? Okay, you don't know that. That's trade-off that has been made. Vendors know, and I'm going to tell you. And maybe the worst one during my test, that's scandalous trade-off. Okay, you see, I'm just sending an exploit. So on the left, you've got what the client sends, what the server receives. In the middle, what the IPS does. So first, I send SYN, SYNAC, ACK, and then I launch my attack. Okay, once again, this stupid signature. What I see is that the IPS is going to send resets on both sides. Okay, with different kind of sequence numbers. So it differently shows, it doesn't follow the session. Or it follows like more or less. And even worse, at the end, the exploit is passed through the IPS to the server. So the IPS just relies on the fact that, okay, with all these resets, we've got a chance that session is going to be closed, and then the attack is not going to be efficient. Okay, we'll find no documentation about that. Of course, you have to audit the system to make sure. So you see, there are a lot of trade-offs which have been made. That's only for performance issues. Performance is a pain, I can tell you. So how to test all those limitations? I did start to write a small tool, which is still very early stage code, which will help you just, well, to test for some features, okay? So it's kind of modular architecture, and you've got different categories of tests. Detection and identification, scan, fingerprinting, evasion, DOS attacks, and false positives. I provide some scripting capabilities. If you want to compare two IPSs, you need exactly the same sequence of tests. You just have to replay the test. Very simple reporting. So I've got the interface. And if you want to test more specifically HTTP limitations, we'll have, first of all, different kind of exploits. Why? Because some exploits are sometimes very tricky in terms of signing without false positive. So if you see the list of exploits, it looks like, well, kind of stupid, like the OSTAT exploit, PHPBB. I think I've got, I don't know. But it makes it possible to test without even you knowing that some regular expression mechanism, some, well, decoding features, just on one simple exploit, without any evasion technique. And then I provide some evasion techniques, URL mutation, so different techniques, and I perform a test before, because sometimes, okay, you have got a lot of mutation techniques, you send the URL and say, hey, it's not blocked. Yeah, but it's not understood by the server anyway, so that's no interest. So here it will test, make sure that the server understands the mutation, and then you will be able to test it with your IPS. Of course, HTTP request smuggling, very important, because a lot of IPSs are not going to be able to detect this kind of attack, so different ways of smuggling, of course, because you've got different mechanisms. But we'll say that most of the time it will be capable, will be able to bypass IPSs, even layer 7 and all this stuff. And insertion mechanism here is based on layer 4 checksum validation. And I've got, well, a tool which is standalone just to test this feature. Very easy. And you see that a lot of IPSs don't test for this kind of feature. And then, well, testing DCRPC, so just the code I showed you, which is included into this framework, just, well, makes it possible to play with these very old exploits with, well, shellcode obfuscation, change the resource name, remote port, bind on multiple interface. So it's still the old way. So it means the Metasploit way. You have to audit it a little bit. I mean, change a little bit the code if you want it to bypass some IPSs. But I know you will be able to do that. It's pretty easy. Context alteration, and, well, of course, playing with fragmentation. So fragmentation is really very fun at DCRPC. So yeah, make it possible just to do fragmentation at layer 4, layer 7, and then do some pipelining. Also a feature just to trigger offload. The first time I discovered this offload mechanism, I was just sending Snort. Sorry. It's not on, through an IPS, so a lot of packets per second, a lot of alerts, and I just launched my attack, and hey, it's not blocked. Why? Because the IPS was just offloading, say, oh wow, that's too much traffic. I pass it, I don't have time to analyze it. So of course, no packets were dropped. I did a test. But my attack just went through. So here, I'll provide a DOS module. Well, it can be used to test for DOS protection, but also just to test for offloading of the IPS. Because, you know, most of the time, they're small packets, so it's going to use a lot of your network processors, maybe your CPU, and it's going to trigger offloading pretty easy. And Snot is not included into the framework, but you can do it yourself, okay? With this DOS mechanism running in the background, you will essentially offload or overflow network processors. With Snot, it will be the signature engine, so usually a CPU or some specific ASICs that's going to be overloaded. But anyway, traffic is going to be bypassed, so no problem for you. So, as a conclusion, IPSs can be detected. Okay, we saw that. They can be bypassed, and you can pretty easily generate denial of service attacks. And that's because of cost. That's, I think, most important thing. Physical limitations. We saw that with hardware, design, all this. And of course, the CSO's fear of unemployment. Just, first of all, the traffic must go, then security. So, okay, is that all that bad? I mean, what about these IPSs? No, it's not. Just the problem is that you have to be aware of the limitations, once again. Don't believe that you've got the magic box. Don't believe that the IPS is going to be able to block any kind of attack with any kind of obfuscation technique in any context. No. Just acquire an IPS for what you want. You need to get protection against SYN floods, then get the best IPS you can find for SYN flood protection. And don't ask this IPS in the meantime to do bandwidth management, to do, I don't know, signature analysis, and all this. So you need to know the limitations, so it will be possible for you just to, well, to get the right solution, and you have to understand it. You have to understand which will be the limitations, because even if you've got the best product for this problem you face, this product have limitation. Maybe it can be detected. Maybe at some point can be offloaded or overloaded, all this. Then you have just to realize that's kind of logic. Okay, it's logical. I mean, there's no perfect solution. When you've got a limited amount of memory, and this memory is completely full with frags, what do I do with the next frag that comes? Either I drop it, so I drop packets, or I forward it. It's logical, and just normal. And also you have to accept the fact that it may be expensive to have a good product, okay? That's one problem with vendors. They're fighting for low prices. It means they're going to make some choices which are not good, maybe. But that's the only solution to have those products not too expensive, because we know customers are not going to buy too expensive products. Well, I can understand them sometimes. And of course, you have to know what you want. Okay? And that's another problem. You need some skillful people to test IPSs before you deploy them. But that's another story. So thank you for your attention. If you've got any question. It was really boring. Okay, so thank you.